In this video, we are going to discuss about the techniques or steps to find the inverse Laplace transform from given the Laplace transform axis. So we know the two equations of Laplace transform. The forward equation xs is equal to minus infinity to infinity xt e to the power minus st dt. So this equation finds the Laplace transform output xs, and the second equation xt is equal to 1 by 2 pi j integration sigma minus j omega to sigma plus j omega xs e to the power st d omega. So this equation finds the inverse Laplace transform output when the Laplace transform function xs is given, and this integration is with respect to d omega, and this limit is set as sigma minus j omega to sigma plus j omega. So now when the Laplace transform output or spectrum or frequency domain representation of Laplace transform is given, that is xs is provided, then how to find the corresponding xt or time domain signal xt for the given spectrum axis. So we can use this second equation directly to find the inverse Laplace transform, but you can see that it involves integration of xs. So if xs is a large function, then the integration becomes very complicated. Also the limit sigma minus j omega that we have to determine accurately so that exact xt can be evaluated. So this method of finding the inverse Laplace transform using my equation second equation is very complicated. That is why in practical we generally avoid this approach for finding the inverse Laplace transform. Integration based method is avoided. Instead, we apply the different properties of Laplace transform that we have discussed in earlier classes, and the Laplace transform formulas for some different basic signals that can be used to calculate the inverse Laplace transform in a very easy and simple manner. Now, before finding the inverse Laplace transform, we have to look to the Laplace transform output, that is xs. So it will be given as a fraction, and that function will be in terms of s. So there will be some variable in the numerator and denominator, and suppose we assume that the numerator is a function of ns and denominator is a function of ds. So ds represents the equation or function that is presented in the denominator, and ns represents the numerator of the fraction xs. So if xs is given, then how to find xt using this function? Okay, so for solving this inverse Laplace transform, we can look to the denominator function ds, and based on ds we can select different approach of solving this inverse Laplace problem. So first one is case 1. Here, if denominator function ds has a distinct real roots, then we can use partial factors. So I have given an example here. Suppose xs is given as like this, 1 by s plus 3 and 1 by s plus 4. You can see that the numerator function is nothing but equal to 1. It is a constant, and in the denominator there is a function s plus 3 into s plus 4. So if you put the denominator ds equal to 0, you will find two solutions, s is equal to minus 3 and s is equal to minus 4. So these two are very distinct roots of s. So if ds is solved, then we can get the distinct roots, s is equal to minus 3 and s is equal to minus 4. So this equation falls in the category of first case where ds has distinct roots. So in that case we can use the partial factor method that we will discuss in the next video in details. So where we try to divide this function into separate fraction and then use the properties of Laplace transform to solve the inverse Laplace transform problem. Next, in case 2, if ds has a complex roots or imaginary roots, then try to convert ds to cos omega naught t ut or sin omega naught t ut. So if this function, you can see xs is equal to 1 by s square plus 1. So in this function, if ds in the denominator is equal to s square plus 1, so this function can be written as s square plus 1. You can write as s plus I into s minus I. So its solution will be s is equal to I and minus I. So it is having imaginary roots. So this ds is having imaginary roots. So in that case, we want to use the equation of Laplace transform of cos omega naught ut or sin omega naught ut, so that it becomes in the format of this. So we'll be giving this some examples in the next video, so you just remember the types of the function given and what approach you have to use. In the next case, if the denominator ds has the real roots but it repeated roots, use the formula this t to the power n e to the power minus at ut is equal to factorial n divided by s plus a to the power n plus 1. So I have given this basic example here. Xs is equal to 1 by s square. So if you put s square equal to 0, you will get to solution s is equal to 0 and 0. That means it is having a real root 0, but it is repeated. It is appearing 2 times, 0 and 0. Okay, so in that case, you can use this formula t to the power n e to the power n. So you can see that this s2 square means what? S to the power 1 plus 1. So you can write n is equal to 1. If you compare with this equation, s to the power 2 means s to the power 1 plus 1. So n becomes 1. So in the numerator, you can write 1 factorial and you can divide the whole function by 1 factorial. So that is the approach. If you can convert this function into the type of this fraction, then you can get the inverse Laplace transform as equal to this. So this symbol equal will be, it is not directly equal, you have to write it as Laplace transform here. So inverse Laplace transform of this will give this time domain signal xt. In the last case, if xs is a logarithmic function, so here it will not having the numerator by denominator type of fraction, it will be a logarithmic function. Suppose this example, xs is equal to log of s plus 3 by s minus 6. Here there is no numerator denominator directly, it is a function of log, and for this type of function you have to use the frequency differentiation property of Laplace transform to solve this inverse problem. So I will be giving basic approach for solving in these 4 approaches. Some example I will solve and you please see the next video.